We're now going to test a proportion, and we're going to do it using the p-value approach. Here are 3 tests that we could run. We're going to be testing a proportion, so I'll h sub o, h naught, and h sub a. If I start out here with ha, which is where I like to start, I could say that p, the true population proportion, is less than some number. Now, if I start there where I'm saying less than some number, then I'll come back to h sub o, h naught, and say, what is the opposite of this? What is the opposite of less than? Well, the opposite of less than is greater than or equal to k. So this will be a left tail test, and then, we're going to have our normal curve with the area in the left tail. That's our p-value there. Our p-value is going to be in the left tail. And we are able to write this normal curve here because it turns out then that p hat, all right, p hat, remember what p hat is? That's our observed proportion, the number of observations with a particular characteristic divided by the total number that you have. This is approximately normal if NP greater than 5, NQ greater than 5. All right, so if those conditions are met, then p hat, our observed proportion, follows a normal distribution. We could do this one here. We could run this test, HA, HO, HA. All right, what if we ran a right tail test, then the opposite, right, of some number k, then the opposite of that would be p is, what's the opposite of greater than? Well, less than or equal to k. And this would be a right tail test. Then our p-value would be here in the right tail. It would be that area there. And another test we could run, h naught p, h sub a p. Now, if we do a not equal to test, say it's not equal to some number, well, the opposite of not equal to, this is where we would actually use the equal sign. So this is a two-tailed test, and then what our p turns out to be is that I get half of p over on the left, half of the p-value over here on the right. Now here's our test statistic. It's a z, and it is observed p hat minus assumed p divided by the standard deviation. Now the standard deviation for proportions, maybe you remember, is p q all over n. Let's attempt this problem here. Apparently it comes from the focus problem at the beginning of the chapter, but here's what it says. Recall that Binford's law claims that numbers chosen from very large data files tend to have a 1 as the first non-zero digit disproportionately often. In fact, research has shown that if you randomly draw a number from a very large data file, the probability of getting a number with 1 as a leading digit is about 0.301. So about 30% of the time, you get a number with 1 as a leading digit. Now, suppose you're an auditor for a very large corporation. The revenue report involves millions of numbers in a large computer file. Let's say you took a random sample of 215 of those numbers and from the file, and R, the number, 46 of the entries had a first non-zero digit of 1. Let's write this down first of all. So I've got N is equal to 215, and R, the number of successes, the number of things we observe with our characteristic, having a 1 as a first digit, is 46. Now, right away, I know I'm dealing with proportions, so I don't really have to do this, but I'm just curious, what is p hat? What is the observed proportion of digits having 1, of numbers having 1 as the first digit? Well, it's going to be R over N, so this is 46 over 215, and that comes out to about 0.214, say, 0.214. Now, the problem goes on to say, down here, let P represent the population proportion of all numbers in the corporate file that have a first non-zero digit of 1. Test the claim that P is less than the 0.301 that we saw up here. So there is at least some evidence for it, right? We're getting a p-value of 0.241, and the assumed value is 0.301. And 0.241 is surely less than 0.301. So let's set up our test. Here's step 1. H naught states that, now it's about a proportion, so I'm just going to write a p. Now, step 2, because this is how I usually do things, I get that last. H sub a states that. Now, what we want to know is this. Right, try to get this one first, because that's our claim. Test the claim, that's our claim, that p is less than 301. All right, so that p is less than 0.301. So what does that mean for this one here? Well, what's the opposite of this? What's the opposite of less than? Greater than or equal to 0.301. Now, we'll go straight to the calculator. Press your stats key, over to tests, and select item number 5. So item number 5 is one proportion z-test. So when you select 5, here's what comes up. All right, so what's our p-naught? Our p-naught is 0.301. So put in 0.301. And then x, all right, now x, the calculator doesn't say it, but x is the r. Okay, so how many do we observe with a particular characteristic? That was 46, right? 46 with a leading digit of 1. N, that was our sample size, that was 215, so put a 215 there. Now what kind of test are we doing? So you look over to your alternate hypothesis. We're running a less than test, so I'm going to come over here and I'm going to choose less than, right? So get your cursor on there, press enter, and then down to calculate, press enter. Now when I pressed enter, here's what I got. So it comes back and tells me, all right, I'm doing a less than test, less than 0.301. Here's my z value. Now we'll talk about that in just a minute. But here's the p-value, right? This is the one that we are interested in because we're doing a p-value test. We're getting 0.0027. And then it tells us that p-hat, the observed proportion, is 0.2139. Now that's what we computed over here, right? Just for fun, we got 0.214. So we got the same value. And then it tells us that our sample size was 215. So what do we do with this p-value? All right, so you may remember what we did before is, and you may just know what to do here, but I'm going to compare p to alpha. So I'm going to write a little table, p, alpha. P is 0.0027, alpha is 0.01, and clearly 0.0027 is less than 0.01. So we have that P is less than alpha, and that implies that we should reject H naught. And just to review, here's my way of remembering this. If it's less than, I'm thinking small. And it's a p-value, small p, p for probability. So I have a small probability. And a small probability, I'm thinking it's unlikely. And if it's unlikely, but I'm seeing it, I'm seeing something that's unlikely, I'm going to reject H naught. So we're going to reject H naught, right? We're going to reject H naught. Now what is H naught? All right, so bring it back here, follow it all the way back to my hypothesis. H naught says that P, the proportion, is greater than or equal to 0.301. We're going to reject this. So if we reject this, we're going to go with the alternate. So we are rejecting the 0.301. We're going to reject this 301, and that means that we're going to go with the alternate, which is P is less than 301, which is exactly the claim, right? This is the claim right here. Remember when you read the problem, let's go up and look at the problem here. The problem says, test the claim that P is less than 0.301. So that's our claim. So we're going with the claim. So let's write up a conclusion to match that. All right, so there's a lot to write here because the question is so long. So I'm going to answer it in terms of this question here. So I'm going to say, at alpha equals 0.01, this sample indicates there is enough evidence to support the claim. Now I'm just writing the words right in the question. There's enough evidence to support the claim now that the population proportion of all numbers in the corporate file that have a first non-zero digit of 1 is what? Okay, is, see if I can even write that, is, look what we're doing. We are rejecting H naught and we're going with the less than. So I'm going to say is less than 0.301, is less than 0.301. Now, we're done with this problem, but if you just need to know what this z is, the calculator is giving us a z. What is that? Okay, I'll explain that. Just take about a minute. If you do an inverse norm on your calculator, you do an inverse norm, and then what you get is area, you get mu and sigma. All right, now this is a standard normal curve, so mu is 0, sigma is 1. But if you put in this number right here for the area, all right, so for the area, put in 0.0027. Here's what comes out, negative 2.78. And that negative 2.78, that is the z value that corresponds to the p value. And if we draw a picture, that p value is right here at negative 2.78, and the area under the curve there it is, the 0.0027. So we're now done with this section.